All right, we are back for part 2. These exciting times. All right, so last we left, we were talking about Slater's rules and how to calculate Z effective. And we're going to come back to that and how that relates to other things here in a little bit. But before we do, I want to get into aberrations in the size trend. So generally, you can figure out what atomic size is going to look like just based on things their positions on the periodic table. But the size trend doesn't work for a certain group. And you may suspect what group of elements that is. Based on how I generally refer to this particular group. And surprise, surprise, it's the transition metals. Okay? And what we find is that generally they're all the same size, about. Going left to right. So as I go left to right across the table, and I get to the transition metals, things are pretty much the same all the way across. And why would that be? Okay. Our first clue, we're going to look in the electron configuration. Okay. So remember what we said at the beginning of the last video. And the idea is that a larger n value means a bigger orbital. Okay, so bigger being the operative word here. Okay, so as I go left to right across the periodic table, I'm adding electrons to which orbital? The d orbital. Right? And the d orbital has a lower n value than the s orbital does. So the s orbital is effectively the one on the outside controlling the size of the atom. Okay? So as I'm filling up my d orbital, it's filling up on the inside and not really affecting the overall size of my atom. So let's take a look at a couple of examples. If I have for example, iron has an electron configuration that looks like argon, 4s2, 3d6. Okay? My 4, that's my largest orbital. Right? It's my largest orbital shell, but it's slightly lower in energy. Which is why it fills first. Okay, so that's why we get the 4s2 in front of the 3d in the electron configuration, because it's slightly lower in energy and it fills first, but it's the largest shell. Okay, my higher energy shell, slightly higher energy shell, is an inner inner shell. Okay, n equals 3 versus n equals 4. That one is smaller, right? Right, so this is the idea, is that basically the shell on the outside is the one that's controlling the size. So as I move left to right across the table, my outer shell stays the same while I'm filling more electrons in the inner orbital. Right, looking at a couple of examples, if I have cobalt, argon 4s2, 3d7, and nickel, the one right next to it, 4s2, whoops, wrong thing, not going there, argon 4s2, 3d8. These elements are roughly the same size, okay, because that 4s is on the outside. 4s is outside and stays the same. Okay, so the 3D fills on the inside. All right, so our lovely friends, the transition metals, love to buck the rules. So going left to right across the table, we don't see a really big difference between elements on the left versus the elements on the right. So if you want an example of that, take a look at page 263, and you'll find that for atomic radii, it's a really nice chart. You'll see that like iron, cobalt, and nickel, iron's at a 1.32, cobalt's a 1.26, nickel's a 1.24, and then you get to copper and it goes back up to a 1.32 and it's a 1.22. Everybody's basically in the same like 1.3s and 1.2s all the way across the most of that transition metal series. Right? So transition metals, yay! Right? So we're going to switch gears a little bit and ask the question, why do ions form? Right? And the answer to that can be found in the electron configurations. Okay? And the point is that the motivation is to get a full valence shell. All right? So if I look at an anion, for example, the way this is going to roll is that I'm going to take an electron and I'm going to add it to a neutral bromine, right? Which has an atomic radius of approximately 114 picometers. Okay? And what I get is a Br minus that is now 196 picometers. Okay? And there are a couple of reasons for that growth in size. One reason is that when I add that electron on, I haven't changed the Z effective at all. So that that new electron has a lower Z effective. Okay? And remember, the Z effective controls how tightly things are pulled in towards the nucleus. So if it's got a low Z effective, that new electron can fly out farther away from the nucleus. Okay? A simpler idea is that anions simply have more stuff. Okay? It's kind of like blowing air into a balloon. Like if you imagine the air inside of a balloon as the number of electrons that are already there, if you put more air into that balloon, it's going to get larger. Okay? So anions get bigger. Right? Cations, on the other hand, it's a lot like letting air out of a balloon. Okay? If I start with a neutral sodium, and my circles are really good, aren't they? With a radius of 186 picometers. If I take off an electron, now I have an ion that is 99 picometers, plus an electron wherever that happened to have gone. Okay, and sodium, when it does this, it quite literally loses an outer shell. Right? So the moral of the story here, friends, anions are bigger than their neutral friends. Okay? Anions are bigger. Cations are smaller. Okay? So let's take a look at the electron configurations and see if we can figure out why this even happens in the first place. Okay? So full or half full subshells are particularly stable. Okay? So, and the reason for that is due to a thing referred to as parallel spins. All right. Let's take a look at what in the world does that mean. All right. So if I look at bromine, for example, it's going to have an electron configuration 4s2, 3d10, 4p5, right? So if I sort of write this out in blocks, which is always fun to do, there's my 4s, 2, 3, 4, 5, and my p's. Right, so here's my 3D, and here's my 4p. All right, so when I go to fill this, I'm going to put my 2 electrons in my 4s and my 10 electrons in my 3D. And then I'm going to have my 5 electrons in my 4p. Right? Now, what I've got here sitting in front of me is that all of these electrons, these are all paired spins, one up, one down, right? So I have 2 times the spin parallel. Right? So I've got all of those electrons are parallel spins. They're very stable, right? So this acts like a core. Right? Now, looking out here at my 4p, if I put one more in there and make that causes this to be Br minus, filling that subshell all the way is more stable. Okay? So bromine has an incentive to pick up an electron because filling that shell all the way makes bromine more stable. Okay? And it also gives it the same electron configuration as a noble gas, now doesn't it? Right? Noble gases are the way they are. They don't react with other things because they are super stable. They have that full p shell. Okay, that completely full p shell makes noble gases very stable. Let's look at another example. A different example. On the other side of the box. Sodium. Sodium's a great one. Has 1s2, 2s2, 2p6, 3s1. Right? The electron configuration. 2s. My boxes are good too. I'm really good at drawing shapes. That's why I'm not a visual artist. You all get the benefit of my attempts. Here's my 2p and my 3s. Okay, and I'm going to go ahead and fill electrons in these guys. So I've got 2 electrons here, 2 electrons here. My 2p is completely full. And then I've got 1 electron right there. All right, this is a full subshell. Which means that that particular subshell is very stable. Right? So if I get rid of this guy, I can get to a full subshell. Right? Making that bromine, not bromine, sodium plus. And guess what? Now it has the same electron configuration as a noble gas. Are you seeing a trend here? Hopefully you are. Okay? So there's a very good reason for these things to make ions. If sodium drops off an electron, it becomes more stable. If bromine picks up an electron, it becomes more stable. Okay? Right, so coming back to our old friend Z effective, it drives other trends as well. Okay, and one of those that the trends that it drives is the one of ionization energy. Energy. Okay, and we'll call this IE. For ionization energy. Okay, and the rigid definition of ionization energy looks like this. And we always write the definition of ionization the same way. So if I'm going to do, for example, oxygen gas losing an electron. This is a weird example because oxygen doesn't really do that, right? But this is the rigid definition. And in the other aspects of the definition is that this is always a gas phase. Okay? And the important thing about this is how stable are the electrons? That's the big important question to determining ionization energy. Okay? That's a big important one, right? And with this definition, we'll have an associated enthalpy, delta H equals IE1. And what that really means is that is the ionization energy for the first electron removed. Okay? So when dealing with ionization energy, we're always concerned with how stable are the electrons on the outside. Okay? Another important aspect is that ionization energy is always positive. Okay? It's always an endothermic process. Okay? The reason for that is it costs energy to pull off an electron, to remove electrons. Okay? Always. This is always a thing. Okay? Ionization energies will always be positive. They'll always be endothermic. Now, what we're going to find is that some ionization energies are lower, meaning that it doesn't take very much energy to pull something off, versus other ionization energies that are much, much higher, which means that it costs a lot of energy to pull something off. Okay? All right. So the trend for ionization energy, so the periodic trend, is left to right. Ionization energy goes up. Okay? What else goes up going left to right? Z effective. Come on, stop arguing with me. Right? Now Z effective, remember Z effective is how tightly electrons are being held to the nucleus, right? So as Z effective goes up, that attraction increases. That also means that the atom is holding on tighter to its electrons, so it costs more energy to pull electrons off. Right? And that is a big important thing. Higher Z effective holds tighter. Right? So remember, the idea is that ionization energy is the energy that it takes to pull something off. So if Z effective is holding tighter to the valence electrons, that's terrible valence. That makes it harder to pull electrons off. Okay? That's a very important aspect. That Z effective goes up, that also forces ionization energy to go up. Right? The trend going top to bottom the ionization energy trend top to bottom, the idea there is that more shells mean the valence are farther away. Right? Our atoms are getting larger. If the valence are farther away, it's easier to pull off electrons. So it costs less energy to pull off electrons for larger atoms. Okay? Greater distance from the nucleus. Means it takes less energy to pull off an electron. Okay? That says pull off an electron. Right? Now let's take a look at what the trend looks like sort of graphically, because that's going to show us some interesting things. Working at home is such a funny thing. Right now there is a pair of large old basset hounds outside that I can hear because my windows are open, and they're just barking up a storm in their wonderful basset hound way at something out there. It's very comical. I don't know if you can hear it. Okay, so looking at ionization energy, okay, that's what our E here is ionization energy in kilojoules per mole versus atomic number. So down here, around at the very bottom, we're going to have sodium at roughly 496. Okay. And then we come up and we get to magnesium at about 738, and this is not to scale. And then it drops down a little bit to aluminum at 578. And it goes up to silicon at about 787. And it goes up again to phosphorus at about 1012. And then it drops sharply here. Well, not sharply, but it drops some to sulfur at about 1000. And then it climbs again to chlorine at about 1250. Okay, so we have this kind of like zigzag pattern to the ionization energy. And what's the deal with that? Why the jagged trend? Why isn't it just a smooth increase in ionization energy as we go across the table? We're going to get back to the whole half full, completely full shells makes a difference. So let's look at the electron configurations for the things that we just wrote here. Ground state electron configurations for these elements. Okay. So sodium is neon 3s1. Magnesium, neon 3s2. Aluminum, neon 3s2 3p1. Silicon, three s2 3p2, excuse me, yeah, 3p2. Phosphorus. Notice that these all have the same shielding, that neon shielding, which sounds like something out of a sci-fi novel. Look out, I've got my neon shielding. Stay back. Neon 3s2, 3p4, and I'll show, just bear with me. Is that right? Hold on. Yeah. Okay. So we're going to stop right there, and I'm not going to go all the way through to the noble gas. But looking at what my orbitals look like as like little boxes, here's my 3s, and I've got one electron in it. That guy is easy to pull off, right? If I remove that 3s electron, I'm at neon, and I'm very stable. Okay, so that's going to be really, really easy to pull off. Look at magnesium. Now I've got two. Now I've got a completely full 3s shell. that's pretty stable. Also, more is the effective. Slightly more difficult. Right? I'm not going to be able to do this. Right? So here, this is going to get really tight. I think I drew this all too small. This one's going to be a little easier. The P is higher in energy. Right? So with that p orbital, there's one electron above a full 3s shell, right? 3s is, it's going to be more stable because it's the full one. P now has shoved an extra electron in there, caused a little bit of extra tension. So aluminum is going to be perfectly happy to get rid of that outside electron. Not a problem. Right? Now, here we are. We've not really changed much, but now we're getting more Z effective again. Right? We get to the 3p. The 3p, guess what we're faced with? Right? Half full P makes this a little more difficult. Right? That half full P is more stable. I should be labeling these. All right. When I get to silicon, this is going to be a little easier. If I lose that P, I get back to half full. Okay? So there's a trend in that ionization energy that has to do with, as you approach the half full stage, you're building up tension and your ionization energy is going to go up. And then once you get to your half full stage, that's when it's going to be the most difficult because things are particularly stable. Okay? And to reword that a little bit, as you are approaching the half full or completely full, you're building up Z effective, and that's the only thing that's building. And then once you get to half full or completely full, things are very stable, and so it wants to hold on to the electrons that it has. Then once you go past that stage, now it's easier again to remove electrons. All right? So this all has to do with the filling of these orbitals and why they are particularly stable in any particular way. All right, so up here at the top, I talked about ground state. I labeled this as ground state, right? So let's talk about not ground state. All right, we'll do it in blue. Talk about excited states, okay? So the ground state for carbon, and I'm back to my boxes again because they're so good. Go ahead and cringe, throw things at the screen, that's fine. Oh no, Dr. Lion, no more boxes. All right, but I'll have 2 electrons facing up in that outside place. Excited states, on the other hand, we've got a couple of versions. We can have one that looks like where we move this guy, where I move this electron to a higher level. Okay. Okay. So if I promote an electron from a lower level to a higher level, I've increased the energy by promoting an s electron. Okay. So there's one version of an excited state. Next way that we can do it is we can borrow it and so if I start with the regular one, so if I borrow it and shove it in here, instead of putting it in its own box, now I've got higher, even higher electron, because electrons don't like to be paired. All right, if they can help it, they don't like to be paired. So by shoving it in the box with another electron, it's like forcing 2 cousins to share rooms at Christmas time. Cousins that don't like each other. Sorry for my analogies. They're all so weird. Not the light blue. So the third way that we can do an excited state is to simply flip one that's already in its current place. Okay, and that causes it as an excited state because parallel spins are more favorable. Okay, so by forcing it to go the opposite spin, I've created an excited state. All right. So we've talked a bit about ionization energy and the trend in ionization energy, but that's all been for valence electrons. Core electrons, on the other hand, are really, really hard to remove. Okay? It really doesn't happen. Okay? So sodium is always a simple example, so we'll look at him again. It again. Let's stay neutral in this world, folks. Right? So ionization energy 1 for sodium, so pulling off that 3s electron, takes us about 496 kilojoules per mole. All right, and that's to remove the 3s1 electron. Okay, so if I remove that 3s1, now I'm left with just the neon ones, right? Just the core electrons. So if I try to take off a second electron, that's going to cost me 4,600 kilojoules per mole. Okay? That's what it costs to pry off a core electron. way more expensive, way more energy. 1,000 times more energy. Okay, so pulling off core electrons really doesn't happen in nature. We've been able to do it in laboratories, which is why we know what these values are. But left to their own devices, this never happens in nature. All right, so let's look at another example. Aluminum. Looks like neon, 3s2, 3p1. Right? So ionization energy 1, 580 kilojoules per mole. That puts me at the 3s2. Ionization energy 2, 1800. Now I'm at 3s1. Right? So noticing a trend here, for each electron that I try to pull off, things get a little bit more expensive, right? So at IE1, this is aluminum plus, right? At IE2, I'm an aluminum 2 plus, and when I get to IE3, I've depleted my valence, and I'm at aluminum 3 plus. If I try to go one step farther, it's going to cost me 11,600 kilojoules per mole. Aluminum 4 plus doesn't form. Okay, so this has a lot to do with why ions stop at certain places. Aluminum's got tons more electrons on it. Why shouldn't it be able to do 4 plus or 5 plus or 6 plus? Because it costs way too much energy. Okay, aluminum doesn't form a 4 plus ion it just costs too much energy. Okay, too much energy to ionize that far. Okay. So, last topic, and it's kind of a fun one, because it's getting away from some of these trends things, and it's the concept of magnetism. Okay, so there are two types of things. There are things that respond to magnetic fields, and there are things that don't respond to magnetic fields. And some things respond well to magnetic fields. Some other things that respond to them don't respond as well. But it's really kind of a do or don't thing. And the terms we use for those situations are paramagnetic and diamagnetic. Okay? And for a long time it took me a long time to figure out which was which. And what I ended up sort of settling on is that para means unpaired. Okay? Para means unpaired electrons. And that, my friends, makes something magnetic. Okay? The idea here is that unpaired electrons respond to magnetic fields. Okay, so if you don't have any unpaired electrons, the thing is not going to respond to a magnetic field, right? For example, let's do let's take a look at the electrons for carbon again, since we've done that for a bit. Don't try to fix my box. All right, so my electrons look like that, right? Those are paired. Unpaired. Right? I've got two electrons that are all by themselves in their own boxes. Right? So carbon does respond to magnetic fields. It is paramagnetic. Okay? Now, you go out and you hold a magnet up to a pencil lead, it's probably not going to do much. But we have ways to measure response to magnetic fields. Okay, and it's called a thing called a gooey balance, which is just fun to say. But we have ways to measure response to magnetic fields, and carbon does in fact respond to magnetic fields. All right. Now, the other side of the equation, the other side of the coin, diamagnetic. Diamagnetic is all paired spins. Okay? In other words, not magnetically susceptible. Okay? Does not respond to magnets. Talk about zinc. Zinc has an electron configuration of argon, 4s2, 3d10. Right? And we can take and draw our boxes. Here's our 4s. Here's our 3d. And I should have done this in a different color to begin with. But here's my 3d10. Okay, these are all entirely paired. No single electrons by themselves. Okay. All paired means that it is not attracted to magnetic fields. All right. I feel like there's some kind of dating joke in here somewhere where when everything's paired, they're not attracted to anything else. I don't know. But I'm going to try not to take that any farther than I already have. So let's take a look at something that is, so like we said, if you hold a magnet up to a bunch of pencil leads, even though they're made of carbon, you're probably not going to be able to move them with a magnet. Let's look at something that we all know is very magnetic. Iron has, in its electron configuration at the end of it, has a 3d6. Right, so it's going to have four unpaired electrons. That makes it definitely magnetic. Specifically, iron is paramagnetic because it has unpaired electrons. Okay? So that pretty much does it for my notes. I think I've covered just about everything. We've covered atomic size trends. We've covered ionization energy trends. Have we talked about electronegativity? Is that in this chapter? Electronegativity follows the Z effective trend. I think that's good. I'm just going before I leave off on this. Let's talk about that. Electronegativity. Gosh, my brain is cooking. I hope you are all taking breaks along the way with these lectures because they are super long. This is meant to be over several days worth of class time, so please try not to assimilate all this material all in one sitting. I realize that the mastering is due tomorrow night, but give yourself some small chunks to deal with this stuff. But electronegativity trends. Right, so electronegativity generally is the ability to attract electrons. Okay, and it goes along with the what we call electron affinity. Okay, so electron affinity and electronegativity, they're very, very subtly different, but in a very practical way, they're basically the same thing. So the ability to attract electrons. And the trend is very simple, is that fluorine is most electronegative. Okay, that's about it. So as you leave fluorine, as you go down the table, so from fluorine, going down, or going left, electronegativity drops off. Okay, that's about it. That's pretty straightforward sort of trend. Fluorine is the most electronegative, and as you go left and down, electronegativity drops off. So things like cesium have the lowest electronegativity, and let's also think about, so if electronegativity follows the effective, let's make sure that that's clear. Fluorine has a very high Z effective. It has a Z effective of 7. Okay, it has really nothing in the way of core electrons, so all of its electrons are being pulled really, really tightly to its nucleus. Right? So if electronegativity is the ability to attract electrons, it makes sense that fluorine would be the most electronegative. Now, on the other side of the table, down by cesium and rubidium, those guys have a Z effective of 1, and they're super big. Right? So they're not going to be able to pull electrons in very well because they're so large. Okay? So small atoms are going to have a higher Z effective than big atoms. Atoms on the right-hand side of the table are going to have more electronegativity than atoms on the left-hand side of the table. So fluorine is the most electronegative, and everything going away from fluorine is that trend. All right, I'm pretty sure that that's it for this chapter. If I've missed anything, please contact me tomorrow or whenever. And I hope you've enjoyed my video, and I hope that my boxes and my bad jokes have not turned you off to watching them. Have a good night.